Consider the diagram that follows, which represents two steps in an overall reaction. The red spheres are oxygen, the blue ones are nitrogen, and the green ones are fluorine. A, write the equation for each step in the reaction. All right, what this drawing represents is a mechanism for a chemical reaction. A mechanism is a series of steps that a reaction goes through in order to turn reactants into products. It's theoretical, can only be proven wrong, but most reactions don't occur in a single step. They occur in a series of steps. When you add the steps together, you get the overall reaction. All right, so this is the collision theory. In order to react, the idea is these molecules, F2 and nitrogen dioxide, have to slam into each other. So that's the first step. So those two, the fluorines have to slam into the nitrogen dioxides, dislodging one of the fluorines and connecting it to the nitrogen to make NO2F. So this is the kinetic molecular theory. These have to slam together in order to react, right? In order to overcome the repulsions between the electrons. They got to slam hard enough to react effectively. We have to break bonds and form new ones. So this is the relationship. If I double the concentration of F, I double the collisions with NO2. If I double the concentration of NO2, I double the concentration of F. So this is a second order rate law, according to step 1. Step 2, this fluorine radical that we made during the first step slams into another nitrogen dioxide and makes another NO2F. So it's a two-step mechanism. The rule is when you add these two steps together, you have to get the overall equation. So 2 NO2s reacting, 2 moles of NO2 reacting with 1 mole of fluorine makes 2 NO2Fs. Okay. C, identify the intermediate in the mechanism. An intermediate is made in one step, all right, that's the fluorine radical, and then it's burned in the next step. So when I add these two steps together, right, fluorine radical doesn't appear in the overall equation. It's made in one step, used in another. So fluorine radical is the fluorine atom that's produced during this reaction is the intermediate. D, write the overall rate law for the reaction if the first step is the slow step, the rate determining step. All right, the reaction, one of the rules for reaction mechanisms is the slow step, right, the one that's holding everything up, waiting around for an effective collision between NO2 and fluorine is what's holding this reaction back. So the rate law for that step has to match the overall experimentally determined rate law. So first order with respect to NO2, first order with respect to fluorine. It's a second order rate law overall. And this rate law matches the first step. Doubling the constant, so I have to wait for fluorine to collide with NO2. If I double the concentration of NO2, I double the opportunity collisions with the fluorine. If I double both the fluorine and the NO2, I quadruple the opportunity for collisions, right? So I get an exponential increase if I double both reactants, NO2 and fluorine. So, second order rate law. Based on the following reaction profile, how many intermediates are formed in the reaction where A turns into C? How many transition states are there? Which step is the fastest? Is the reaction A to C exothermic or endothermic? All right, so answering the first part of this, there's 2 humps. All right, hump 1 goes from A to B. So B is an intermediate. B does not show up at the end of the reaction, right? So it's not a product. It's made in the first step and it must be used in the second step. All right, this is A turning into C. So it's in the swale between the 2 humps. So step 1, right, you got a big hump. Step 2, you got a small hump. There are two transition states where A is turning into B and where B is turning into C. Those are at the top of the hump, right? We're in the process of breaking bonds and forming new ones. The second step is the fastest. It has the lowest hump. So the smaller the hump, the smaller the activation energy, the quicker the reaction. So the slow step in this reaction is the first one. Looking at the overall potential energy change, right? So kinetics is all about the humps, right? The first hump, the second hump, right? In terms of how fast the reaction is going. Equilibrium and thermodynamics is concerned with, am I losing potential energy at the end of the reaction, or am I gaining potential energy? I am lowering the potential energy of this system when I go from A to C. So losing potential energy means I'm releasing heat energy. So this is an exothermic reaction. 17. What is meant by the term rate of reaction? Change in concentration of either the products or reactants over time. That's what rate is. B. Name 3 factors that can affect the chemical rate of reaction. Well, I can do better than that. I can name 4. Increase the temperature, increase the rate. Depending on what the reaction is, sometimes increasing the concentration can increase the rate. If it's a solid and it's interacting and it's a surface area issue, increasing the surface area will increase the rate. And adding a catalyst will increase the rate. C. Is the rate of disappearance of reactants always the same as the rate of appearance of products? Explain. No. Relative rate depends on the coefficients in the balanced equation. So for example, if I'm talking about the disappearance of the rate of disappearance of hydrogen versus the rate of disappearance of oxygen, all right, change in concentration of hydrogen over time, and I want to compare that to oxygen. Well, according to the equation, for every 2 moles of hydrogen disappearing, you're only losing 1 mole of oxygen. So that equates to half the rate. So for every 1 mole of hydrogen disappearing, you're only losing half a mole of oxygen. So it's going slower. So depending on what you're measuring in the reaction, appearance of products, disappearance of reactants, you'll get a different rate. 19. Consider the following hypothetical aqueous reaction, A turning into B. A flask is charged with 0.06 moles of A in a total volume of 100 milliliters. The following data is collected. Time 0, you're starting with 0.065 moles. After 10 minutes, you've got 0.051, 0.042, 0.036, 0.031. Okay. Calculate the number of moles of B each time in the table, assuming there are no molecules of B at time 0, and that A cleanly converts to B with no intermediates. Okay. So A is turning into B. These are my times that I take these measurements. So as A is disappearing, B is appearing. If you're starting out with 0.065 moles of A, you don't have any B. After 10 minutes, the concentration of A went down, or mole value of A went down to 0.051. So if I subtract that from my starting mole value, that's how many moles of B showed up. After 20 minutes, the mole value of A has gone down to 0.042. If I subtract that from what I started, this is how many moles of B have shown up after 20 minutes. And subtract how many moles of A you have left at 30 minutes from what you started. That's how many moles of B were made. And at 40 minutes. So, as A disappears, B is showing up. B. Calculate the average rate of disappearance of A for each time interval in terms of mole per liter second. All right, so just getting the unit right. So from 0 to 10, right, I went down I lost 0.014 moles of A. So it's the concentration of A, change in concentration of A over change in time. So I want to get, this was the mole change. I want to divide it by liters to get it in moles per liter, right? So it was 100 milliliters, so that's 0.1 liters. It was a 10-minute time interval change, but they wanted in seconds, right? They wanted it in terms of mole per liter second. So divide by seconds. And I get moles per liter seconds. So I do the same for the other time intervals, right? From 0 to 10, from 10 to 20, from 20 to 30, from 30 to 40. And these were my average rates between these time intervals. So notice what's happening with the rate, right? Initially, the rate was pretty fast, right, in terms of how much A was disappearing. So through the first time interval from 0 to 10, I had a rate of disappearance of A of 2.3 times 10 to the minus 4 moles per liter second. Then it goes down to 1.5, then it goes down to 1, then it goes down to 0.8. So as A disappears, this reaction is slowing down. All right, C. T is equal to 10 minutes and... Oh, all right, so they want the rate change between T is equal to 10 minutes and T is equal to 30 minutes. What is the average rate of appearance of B in terms of moles per liter second? Assume the volume of the solution is constant. All right. So between 10 and 30 minutes, I went from 0.015 moles of B to 0.036 moles of B. So that's the change in B over 20 minutes. Get it in moles per liter, get it in seconds, and get what the average rate is between these two data points. All right, so later on we'll look at the graphs in terms of what that means in terms of average rate between two data points, like between 10 and 30 as opposed to between 10 and 20. So, to be continued.